Bismillahirrahmanirrahim. So, dear students, today our topic is the Kohlrauch's law. It's also called as the law of independent migration of ions. So, this topic basically I have prepared because some of the student asked for this topic, as normally we expect that in the exams it's asked. So, let us discuss the basics about the Kohlrauch's law. Uh, So first of all, molar conductivity of an electrolytic solution increases with increase in the dilution. This is point number one. Now molar conductivity means conductivity when of the ions which are produced by 1 mole of electrolyte. Electrolyte means once the chemical substance gets dissolved, it gives ions. So it's called electrolyte. If you have 1 mole of ions, 1 mole of that particular electrolyte, and that conductivity due to the ions which are produced by dissolving 1 mole of ion, 1 mole of that electrolyte. So it's called as molar conductivity. That molar conductivity increases with increase in the dilution. Dilution means you add more and more solvent. So when you add more and more solvent at one stage, when the solvent is so much that you all the ions will get ionized, they will get dissociated because they move far apart. Okay? So then we say now this solution has got infinitely diluted. So that is the conductivity. At that time, it attains the maximum limiting value of conductivity. It's called as molar conductivity at infinite dilution. This is point number one. And this molar conductivity at infinite dilution, it is represented by lambda. Subscript m refers to molarity, and then 0 or naught, it refers to the it indicates the infinite dilution, means concentration is almost negligible. So Kohlrauch studied molar conductivities of a pair of strong electrolytes. So what Kohlrauch did, he did some research on various electrolytes, pairs of electrolytes, and then his research is tabulated here. इसको हम देख लेते हैं इस टेबल को. Now this is pair of electrolytes. He studied KCl and sodium chloride, where chloride is common. Then this is the value of molar conductivity at infinite dilution, where the temperature is 25 degree, and this is the unit of molar conductivity at infinite dilution, and this is the difference. Now when you dissolved potassium chloride, when you checked the molar conductivity of potassium chloride at infinite dilution, so the value is 149.86, and in the second case when it studied sodium chloride, the conductivity value is 120.6. So the difference is 3.1. So clearly in both these cases the chloride ion is constant. So the difference is due to sodium and potassium. So clearly we know that sodium is a smaller size and then this potassium is a larger size. So this is because of this difference the conductivity value, the difference arises. Now interesting case is that when you take the same sodium and potassium, but when the ion, counter ion, negative ion is different, it's nitrate. If we check this is the conductivity values, but the case is the difference also is this remains the same. So it indicates that, so he predicted on this data, what he did, he concluded that each ion makes a definite contribution to the total molar conductance of electrolyte irrespective of the nature of other ion. So he says that in this case the sodium has a different contribution in this 149.6, and here potassium has a different this contribution in 149.6, and sodium with the same chloride has a different contribution, and likely in the sodium potassium nitrate, potassium has a different contribution and sodium has a different contribution. So each ion makes a definite contribution to the total molar conductance of an electrolyte irrespective of the nature. It doesn't depend कि इसके साथ कौन सा है, कोई भी आयन हो इसके साथ में, जो सोडियम और पोटेशियम का जो कंट्रीब्यूशन है, that is it has its definite contribution irrespective कि इसके साथ क्लोराइड है नाइट्रेट है. अब यहाँ पे हम देख सकते हैं इसका एक टेबुलेटेड फॉर्म यहाँ पे. So this table clearly shows the difference of molar conductivity for pair of potassium and sodium 1 and 2, this and this, that is same. So for a pair of potassium and sodium, so the contribution of potassium which is here, the same contribution is here. The contribution of sodium which is here, the same contribution is here. अब ये जो difference arise रहा है, it is due to the counter ion, it is due to the negative ion. So likely the same difference is seen in the chloride and bromide parts. इसी तरीके से आप इन दो में देख सकते हो. यहाँ पे जब आप पोटेशियम क्लोराइड था, देखिए यहाँ पे सेम कंडक्टिविटी. When you took सोडियम पोटेशियम ब्रोमाइड, तो यहाँ पे वैल्यू 151. इसका मतलब ये जो डिफरेंस आ रहा है 49 to 51, इट इज ड्यू टू दी ब्रोमाइड. जो पोटेशियम का कंट्रीब्यूशन है दैट इज सेम. सो पोटेशियम in a particular salt or sodium in a particular salt or any other cation in a particular salt, it makes a definite contribution to the total molar conductivity of the electrolyte, irrespective कि दूसरा ion उसके साथ क्या है. So this is actually the Kohlrauch's law. So the statement is that each ion makes a definite contribution to the total conductance of electrolyte, irrespective of the nature of the other ion present. Let's move further. So on these basis, Kohlrauch, he generalized the Kohlrauch's law. So the law is like this: the limiting molar conductivity at infinite dilution for an electrolyte is the sum of limiting molar conductivities of each ion. Means इसका मतलब क्या है? यानी अगर आपके पास एक सोडियम क्लोराइड है, we know that when it is dissolved in solvent, so it gives sodium ions and chloride ions, sodium plus, it gives sodium plus, and it gives Cl negative. Now जो टोटल कंडक्टिविटी होगी इस इलेक्ट्रोलाइट की, इस टोटल कंडक्टिविटी में सोडियम का एक कंट्रीब्यूशन होगा, सोडियम का एक डेफिनेट कंट्रीब्यूशन होगा और क्लोराइड का एक डेफिनेट कंट्रीब्यूशन होगा. दोनों का कंट्रीब्यूशन मिला के इट गिव्स द टोटल कंडक्टिविटी ऑफ इलेक्ट्रोलाइट. लेकिन ये जनरलाइजेशन कब पॉसिबल है? व्हेन द कंडक्टिविटी इज मेजर्ड अंडर द कंडीशंस ऑफ इनफाइनाइट डाइल्यूशन. सो द लिमिटिंग मोलर कंडक्टिविटी at infinite dilution for electrolyte is the sum of limiting molar conductivities of each ion. ठीक, अब कैसे पता चलेगा? Let's take an electrolyte. This is an electrolyte. So the molar conductivity due to electrolyte whose formula is AXBX. AXBX का मतलब for example, let's say it is, मैं example आपको बोल रहा हूँ. AXBX means, let's say it is Fe2 Cl4. मैं एक एग्जाम्पल बना रहा हूं. AXBX का मतलब क्या होता है? Fe एक आयन है, कैटाइन, it's 2 times, and this chloride is also 4 times. So when you have this type of electrolyte, इसकी जो कंडक्टिविटी हो किसकी बराबर होगी? वो होगी x times A. X times conductivity of A, the limiting molar conductivity of A, but it's x times. Likely limiting molar conductivity of anion B, but y times. अब एग्जाम्पल लीजिए आप बैरियम क्लोराइड. सो बैरियम विल डिसोसिएट, बैरियम का आपका x आएगा, x टाइम्स बैरियम. यहाँ पे बैरियम का जो चार्ज है दैट्स +2 एंड क्लोराइड यहाँ 2 है, सो 2 टाइम्स. सो वी हैव टू कीप इन माइंड ओनली दिस स्टोइचियोमेट्री. इट इज 2 हियर बिकॉज इट इज Cl2. सो in terms of equivalent conductivity at infinite dilution, there is another term called as equivalent conductivity at infinite dilution. फर्क क्या है इसमें? Equivalent conductivity means if you have 1 gram equivalent of electrolyte. So 1 gram equivalent of electrolyte, if you if you dilute this, and then the conductivity due to 1 equivalent of electrolyte at the infinite dilution, so that's called as equivalent conductivity at infinite dilution. So you can express it this in terms of this lambda. Now we have to write subscript equivalent and then infinite dilution by this naught. You can also sometimes see by books they write like this: lambda infinite and then you put here equivalent. So instead of naught they will write infinite also, but anyway it means the same thing. So conductivity of an electrolyte, 1 equivalent of electrolyte at infinite dilution is simply equivalent to the same formula, cation plus anion. ठीक है? So now जो application है इसकी, there are many applications, लेकिन जो main application है Kohlrauch's law की, with the help of Kohlrauch's law, what we can do, we can predict the molar conductivity at infinite dilution of weak electrolytes. अब इसका मतलब क्या है? Weak electrolytes ऐसे electrolytes they don't dissociate easily, या they dissociate to the less extent. लेकिन इस law की help से you can calculate कि molar हम उसका, we can also know that even though it's a weaker electrolyte, it doesn't dissociate completely into the ions, But with the help of this law, we can predict what is the limiting value of molar conductivity of weak electrolytes. कैसे? Let us say we have an electrolyte acetic acid. Acetic acid, you know, this is the formula for acetic acid. It's a weak electrolyte. So how can we calculate this? देखिए, acetic acid, if it dissociates, it gives H plus. So the conductivity of total electrolyte is called the molar conductivity at infinite dilution due to H plus, and molar conductivity due to infinite dilution due to acetate ions. Now these two ions we need. How can we know? These two ions हम कैसे obtain कर सकते हैं? One ion we can take from HCl. It's a strong electrolyte. So यहाँ से हमें H plus पता चलेगा. Second electrolyte will take sodium acetate. This is also a strong electrolyte. From this we'll take the acetate ions. ठीक है? अब देखिए दोनों में जो हमें चाहिए H plus and acetate. हमें क्या बचा? Chloride and sodium plus. Now these two will make a salt called sodium chloride, which is also a strong electrolyte. So we can predict the molar conductivity of infinite dilution of this separately, likely molar conductivity at infinite dilution of this salt separately, and molar conductivity of infinite dilution of this salt. So how can we achieve acetic acid? Simply this plus this minus sodium chloride. So you can write this plus any H and Cl ions, the molar conductivity due to acetate ions plus this minus this, so that will give us the molar conductivity of these ions H plus and acetate. So molar conductivity of these two ions at infinite dilution is equal to the molar conductivity of infinite dilution of the acetic acid, which normally doesn't dissociate. लेकिन इन तीन के डेटा से which are the strong electrolytes, by adding these two and subtracting sodium chloride, so we are in a position to obtain the molar conductivity, limiting molar conductivity at infinite dilution of the weak electrolytes also. So there are other applications of also, for example, we can predict the solubility constant and then other things also, but those we will not discuss. This is, I believe, this is enough for your exam purpose. So I hope you understand it. If still you have the questions, we can write down. So thank you.